Okay, so let's continue with the first section of chapter 2. Let's consider the following example. We're given a random variable whose PDF is given by the following. Small g sub t of small t is equal to 1 all over 80, where t is greater than or equal to 0 and less than or equal to 80, and 0 elsewhere. And given that the force of interest is delta, we want to calculate for the random variable z, the net single premium, the variance of z, and the 90th percentile. Okay? We can see that with how the PDF is given, the random variable t has a uniform distribution on the interval from 0 to 80. Okay? And so for the net single premium, we said that it's equal to this integral. But then we're given that the interest rate is the force of interest delta. So v to the t is replaced by e to the negative delta. The PDF of the random variable t, which takes the form of tpx mu sub x of t, is given to be 1 all over 80. And the integral is over all possible values of t, where t would have a positive probability. What we have is that t is from 0 to 80. Okay, so this integral here represents the net single premium of the random variable z. So we just have to evaluate this. So it turns out that the integral is negative 1 over delta times e to the negative delta t, where t ranges from 0 to 80. Okay, so at 80, this would be at t equal to 80, you get this. At t equal to 0, you get negative 1 over delta, but we multiply it by negative 1. So simplifying this, we get the following expression: 1 minus e to the negative 80 delta all over 80 delta to be the net single premium of the random variable z. To get the variance, the first step is to get the second moment, right? And since we have a benefit of 1 unit and delta is deterministic, we can use the rule of moments to get that. So what we just have to do with the expectation of z is to replace every occurrence of delta by 2 delta, right? And so this would now be the second moment. 1 minus e to the negative 160 delta all over 160 delta. And so the variance is the second moment minus the square of the first moment. So this would be our expression for the variance of z. And then we also want to get the 90th percentile, okay, of the of the distribution of z. So it's denoted by this representation, psi sub z to the 0.9. So that 90th percentile is the value of this quantity that satisfies this equation. That the probability that z is less than or equal to the 90th percentile is equal to 0.9. Okay? So what we can do, since we do not know what the distribution of z is, we will convert to our random variable t, since the PDF is given. So the first step is to determine, what we want is to get the probability of this event, right? So we would like to determine the event in t that is equivalent to this event. And this is done in the following way. We note that z is defined as b to the t, right? As b to the t. And then getting the log of both sides, natural log. So you have t log of v less than or equal to log of the 90th percentile. But log of v is actually negative, right? Because v is a number between 0 to 1. Okay? Log, remember, is natural log. Okay? So then t is greater than or equal to the log of the 90th percentile all over log of v. Now let's replace this by h. So we take that as h. So the probability that z is less than or equal to the 90th percentile is equivalent to the event that t is greater than or equal to h. Right? So their probabilities must be the same. But we note that this is 0.9. Okay? So then the probability that t is greater than or equal to h is equal to 0.9. Okay? So that equation, we rewrite this in its equivalent form as an integral, since we know the PDF of t to be 1 all over 80, and that this h will range from, or that the variable t will range from h to the highest possible value of t, which in this case is 80. So we get this integral. And evaluating this integral, we get the following expression. So we then know that 1 over 80 times 80 minus h is equal to 0.9. So we then begin by finding h. This is not very difficult. So this gives us h to be equal to 8, right? But h is log of the 90th percentile all over log of v. So we replace h by that. We cross multiply, we get this equation. Using properties of log, the right side reduces to log of v to the 8. And then we get the antilog of both sides. So the 90th percentile is actually v to the 8. Okay? Here is another example. Consider a 5-year deferred whole life insurance payable at the moment of death of a person aged X. The individual is subject to a constant force of mortality that is mu equal to 0.4 for the distribution of the present value of the benefit payment at delta equal to 0.10. We want to find 1, the expectation, 2, the variance, and 3, the median of the distribution of z. Okay, we first point out that we're assuming that mu is constant, right? So mu sub x of t is equal to a constant mu, which is equal to 0.5. And whenever that happens, the survival function of t, which is tpx, which is we know is equal to this, and now this is fixed at mu, so it reduces to e to the negative mu t. Okay, so tpx is equal to e to the mu, is e raised to negative mu t. And then the PDF of t, we still multiply this by mu, turns out to be mu, right, times e to the negative mu t. This is tpx times mu sub x of t, right? So that would be the PDF of t if a constant force of mortality is assumed on the force of mortality. Okay? By the way, we want to get first the net single premium or the expectation of z for an M-year deferred whole life insurance. Okay? Let's first get a general expression for that net single premium. So we know that this would be the integral from m to infinity of v to the t, but since delta is given, it reduces to this, tpx, which we know is e to the negative mu t, times mu sub x of t, which we know is mu, times dt. So we can rewrite it this way. So this is just by substitution, letting u to be mu plus delta, the quantity mu plus delta t. So this, if you evaluate that, gives us this expression. And if t is at delta, this expression becomes 0, right? Because e to the negative infinity is 0. At m, this becomes m, and negative of negative, we get this expression now for the net single premium under this case. So we plug in what is given. We're given that mu is 0.04. We're given that delta is 0.10. So the expectation takes this form. It's 2/7 of e raised to negative 0.7, which is approximately equal to 0.1419. Okay? And then we want the variance as well. So we can use again the rule of moments to get the second moment, right? So that means we replace every occurrence of delta by 2 delta. Right? So this is the second moment minus the square of the first moment. And that's approximately 0.0301. Okay? And then to get the median, first we note the following. that the random variable z, it is possible that there is a positive probability associated with the event that z is equal to 0, right? Because we note that since this is an M-year deferred insurance, it's a 5-year term insurance, that the event z equal to 0 is the same as the event that t is less than or equal to 5, right? So when death occurs, within the first 5 years, nothing is paid, right? So the event that z is equal to 0 is actually equivalent to the event that t is less than or equal to 5, okay? So it is possible that this is non-zero, and even possible that it is greater than or equal to 0.5. So when that happens, then the median is already 0. Otherwise, if it is less than 0.5, then the median is the solution of this equation. Okay? So let's figure out first what is the probability that z is 0. So we said that the probability that z is equal to 0 is equal to the probability that t is less than or equal to 5. And since we know the PDF of t, so it's tpx, which is this, times mu from 0 to 5. And then when we evaluate this, that gives us 0.1813. So it is positive, but it is less than zero point 0.5. So the median is not 0, right? The median is not 0. So we now find out what is that median by using this equation. We need to break them up to these two probabilities. The left-hand side of our equation, we have to break them up. So the probability that z is equal to 0 plus the probability that z is greater than 0 and less than or equal to the median is 0.5. But we know what this is. This is 0.1813. So you transpose that, we get this equation. Okay, let's drop this part because we will just assume that z is always greater than 0. So we then have this statement. Okay, and then doing what we did earlier, we get the log of both sides, and then what we now have is t greater than or equal to the log of the median all over log of v. Okay, again, this is greater than, it becomes greater than because log of v is negative, right? Because v is between 0 to 1. And then again, if we take this as h, and knowing that the PDF is this, under the constant force of mortality assumption, this equation now, which we got from here, can now be written, this side, this portion, the left-hand side can now be written in terms of an integral this way. So it's from h to infinity, and then you have the PDF of the random variable t. And then when you evaluate this, it gives you this quantity. So e to the negative 0.04h is equal to 0.3187. So first we find out what the value of h is. So we just get the log of both sides. So negative 0.04h is equal to log of 0.3187, or h is equal to this, right? But then we said that h is equal to log of the median all over the log of v. But then we know that the log of v is actually negative delta. So then we get log of the median is equal to delta all over 0.04 times log of 0.3187. And using properties of log, the right side can be written this way. And so getting the antilog, we now get the median to be this expression. But then we note that delta is actually 0.10. So the median is approximately 0.0573. Okay? So I think I'll stop this second video lecture here. we will continue with the next section on insurances payable at the end of the year of death. Okay?